Welcome to yet another session of Accolite Digital Connect, our thought leadership series that focuses on the latest technology trends and business insights featuring our experts. I am Swati Lekha and I will be your host for the evening. Today, we are presenting the second session in our three-part series on machine learning, in which we will focus on the fundamental maths behind machine learning algorithms, learn the basics of hyperparameter tuning, and understand how we can help the machines learn better. And to give us all those insights, today we have with us Priyanka Pal-Shetkar, who works as a product manager at Accolite Digital. Priyanka has experience as a full stack developer and a data analyst in investment banking and the financial domain. She's also the co-founder of Alma Meal, which supports the entrepreneurial aspirations of Indian homemakers through technology. She is a Harvard's Crossroads Emerging Leader and Hindustan Times Pune's Top 30 Under 30 for 2019. But before I hand it over to Priyanka, if any of you have any questions, please put them in the comment section so that we can take it up at the end of the session. So without further ado, I'll hand it over to our speaker. Welcome to the session, Priyanka, and over to you.
Thank you, Swati, for the introduction. Hello, everyone. Good morning, good afternoon, and good evening. I am Priyanka, and I want to welcome you all to Accolite Digital Connect. Today's session is the second part in a three-part series that covers the most important aspects of machine learning. And if you haven't watched the first one, I will suggest you look it up. What I hope to achieve from this series is to build a fundamental understanding of machine learning and its capabilities. So we won't deep dive into the depths of every machine learning algorithm. Maybe we can add more sessions in this series later for that. But from this three-part series, I want us to catch the general theme of how things work in machine learning. And I have gathered resources to help us break the complexities of machine learning into simple, understandable chunks. In today's session, we will understand how machines actually learn and how to train a linear regression model. The concepts that I will walk you through form the basis of almost every machine learning algorithm. The implementation does change a little bit depending on our problem statement and the algorithm that we choose, but the fundamental core will stay the same. I have divided the agenda for today into 4 parts. First, we will recap the most important part of our previous session, which was what is machine learning and what are the different types of machine learning algorithms. Then we will deep dive into the simplest machine learning algorithm, which is linear regression. We will start with understanding what does the machine learn, that is our model parameters. Then we will understand the mathematics behind linear regression and look at how a machine learns, that is training a linear regression model. At the end, I will also give you a sneak peek into our final session of the series. Now, before we begin, I do want to give you a heads up here. We won't be looking at the code behind the algorithm today. My goal is to help you understand how the algorithm works under the hood. So if you already have an idea about that, then the session, though I would suggest that you stay back. With that, let's get started. So in the previous session, we understood what machine learning is. It basically is an approach to automating repeated decisions that involves algorithmically finding patterns in data and using these to make recipes that deal correctly with brand new data. We also looked at the 3 different types of machine learning algorithms, which is supervised, unsupervised, and reinforcement learning. Now, in supervised learning, we have a labeled data set of input and output, and our function maps input X to output Y. Today, we are going to take a look at linear regression, which is an example of a supervised machine learning algorithm. The second type, unsupervised learning, is when we don't have a labeled data set. We just have some input data, and our algorithm's goal is to find meaning in the underlying data structure. And the final type is reinforcement learning, which works like a reward penalty system, where our input is a set of state action pairs, and the goal of the algorithm is to maximize the rewards and minimize the penalties. Now, with that refresher, let's begin today's session. Let's say you work at a very old company where everyone relies heavily on word of mouth sales and they don't focus much on marketing. You, as the new marketing head, understand the impact of marketing on sales, and you want to convince your CEO and senior management that they need to increase the marketing budget. You know your pitch would be effective if you have data that supports your hypothesis. So you go on a data collection spree and gather comprehensive data on marketing cost and sales for your own company and many other companies in your domain. For simplicity's sake, let's say we only have the following information. Now, to convey your point effectively, you decide you will create a machine learning algorithm that helps you estimate how marketing cost impacts sales. Now, to help you understand the fundamentals today, we will work with linear regression algorithm, which is the simplest and one of the most powerful machine learning algorithms out there. Now, despite it being simple, what we learn here about the training process can be extended to most of the other powerful machine learning algorithms as well. So, what is our goal here? What is linear regression and what does it do? Literally speaking, linear means in a straight line, and regression is a statistical method that helps us define the relationship between two or more variables. Now, to put it simply, if this is our data spread, that is a plot of our marketing cost versus sales, then linear regression will help us find this blue line, which would be the best fit through our data. And if we are able to figure out this blue line, then we will have a model that fits our data and helps us predict what the sales value would be for any given marketing cost. And that's what we want, right? So linear regression basically helps us achieve two things here. First, it helps us find out the cause and effect relationship between our input and output data. That is, in our case, it can help us answer the question whether marketing actually affects sales. Secondly, it also helps us in forecasting or prediction. That is, in our case, it will help us answer how much additional sales will we get if we spend an additional X amount of money on marketing. For our specific example, we are using only one single input variable X, which is our marketing cost. But there can be as many input variables. That will be a multiple linear regression. Today, we will be looking at simple linear regression. So let's represent our blue line mathematically. We can write it as y is equal to a plus bx, which is the standard equation of a straight line. Now here, x is our input, that is our marketing cost, and y is our sales amount, that is our output. So what are these two other terms, a and b? A here is the intercept of the line, that is where the blue line cuts the y-axis. So for our example, it's basically the value of sales when the marketing cost is 0. B here is the slope of our line, which is the measure of how steep the line is. And in our case, it tells us how much sales value changes with 1 rupee change in marketing expense. And this line is what we call our machine learning model. Now let's take a step back. Take a look at our model or the equation of this line. We have our input X from our training data. Now, if we need to predict Y for any given X, then what do we need to make this prediction? Yes, we need the values of A and B. We already have X. And if we are able to find the values of A and B, then the equation of our line is complete. And we can use that to find the value of our output Y for any given input X. A and B here are called our model parameters. And this is what our model learns. Our model will find the best values of A and B that helps us fit our input X to our output Y. Now that we know what our model is going to learn, let's move towards the how of the learning and understand how our model trains under the hood. Typically, if you're new to something and you want to learn it, like maybe you want to invest in the stock market, how would you go about it? On day one, you would start with some initial understanding, and on the basis of that, maybe you buy a stock. But say, due to some factors you had not considered, your analysis was a bit off and you lost some money. So on day two, when you will come back to invest, you're most likely to learn from that mistake, the one that you did on day one, and not repeat it, right? That's exactly what our model does. So our model will start with the initial random guess for the values of A and B. Say, for example, A is equal to 10,000 and B is equal to 3. Now let's input this into our equation of the line to get our first guess at the best fit blue line. And that would be y is equal to 10,000 plus 3x. Now the second step would be to test this guessed model. So let's calculate our predicted output y for some value of x. So for marketing cost of 20,000, if we calculate the value of y based on our equation y is equal to 10,000 plus 3x, we get a sales value of 70,000. Okay. But hold on. We do have the data which we had gathered before we even begin training this model. After all, machine learning is learning from data. So our third step would be to compare our predicted value with our actual value from our data, which is our labeled output. So let's look it up. Now from this data, we can see that for the marketing cost of 20,000, our sales revenue was actually 2,80,000. But we got an output of 70,000 based on our initial guess. So we have an error of 2,10,000, which is the actual minus predicted sales. And we can safely say that our initial assumption of A and B is way off, and that is bound to happen. And if we plot our predicted line, that is y equal to 10,000 plus 3x against our best fit line, then we can clearly see the difference here. And we need to fix this, right? But how? This is where we begin training our model on the data that we have. Now, to fix our red line, we have to adjust our model's values of A and B to reduce the error as much as possible and bring our predicted value closer to our actual value. And we will be doing this using the cost function, which is a measure of how wrong the model is in estimating the relationship between our input X, that is our marketing cost, and our output Y, that is sales. So in our case, let's assume the cost function is simply the mean error, which is the difference between actual and predicted value of sales. Now the goal of our model is to find the values of A and B such that we minimize the error or our cost function. And we will keep on repeating this process and keep on updating the values of A and B until our error reaches its least value. That is, until our red line finally starts representing the blue line. And what is the role of our cost function here? We cannot just update A and B randomly. This is not a guessing game. We need a measure which tells us we are going in the right direction. And our cost function does exactly that. It's like a KPI, and it directs us to reach the optimal solution. It acts like an indicator of how our model has improved. Now, there are many cost functions in machine learning, and it depends on the type of algorithm that we would use to choose our cost function. It's pretty important to decide on a good cost function because it is guiding our machine learning model to achieve the best result. Technically, we would use mean squared error as our cost function for our linear regression model, but I'm keeping it simple here by using the mean error for our understanding purposes. Okay, now that we know that we have to minimize our cost function to achieve our goal, the next question is, How is the cost function minimized? And that's where gradient descent will step in. But wait, what is this gradient descent? And what do we even mean by a gradient? A gradient measures how much the output of a function changes if you change the input a little bit. So it basically represents how steep a slope is. So if we were climbing this mountain with a bike, then this black line is our gradient. Now, when we go up the mountain, then our gradient is positive. When we are going down the mountain, then our gradient is negative. And when we reach the bottom of the mountain, where the surface is flat, then our gradient is 0. And that's what gradient is. The gradient descent is an optimization algorithm that helps us find the minimum value of any given function. In our case, we are going to use gradient descent to find the minimum value of our cost function. So let's see how it works. Imagine you are at the top of a mountain and you want to climb down. However, you can't see the path very well because of bad weather, say. So how would you climb down? Your best bet would be to feel the ground in every direction and take one step at a time in the direction where the ground is going down the fastest. So if you are here, you will check which direction will take you down and take a step in that direction. And if you keep on repeating this, you will end up at the bottom of the mountain. That's what gradient descent does too. In our case, the mountain is our cost function. Initially, we are at a point where our error is some finite value, like here, where our cost function is say 100, for example. Gradient descent will help us reach the bottom of this cost function mountain. That is, it will help us bring this value of 100 down to 0. Now let's see how it will do that. Let's plot our cost function and update it with every time we take a step down the mountain. So we have our cost function here on the y-axis and the step number on the x-axis. Now assume we are here at our initial position P, where our cost function value was 100. Now with every step that we take, we want to move towards this green mark, which is our final position, where the cost function is 0. And we can represent what we are doing in the form of an equation like this. We are at our current position P, and we want to update our position to move to our next position P next. Why minus? Because we are trying to find the minimum value here. That's why minus. Further, this update in position can be written as alpha times a derivative of a cost function. Now here, J is our cost function and theta basically represents our values of A and B together. And this derivative term is basically our gradient. Now don't get baffled by this strange looking terms here. Think about it in this way. If we have to climb down a mountain, we basically need to take care of two things. First is the size of the steps that we take. And second is the direction in which we are taking the step, right? Now this weird looking term here, that is our alpha, is our learning rate. And it accounts for the size of our steps. And the second term, which is our gradient, accounts for the direction of steepest descent. Hence the name gradient descent. Now in gradient descent, we'll keep on repeating this process of updating our position until we reach our minimum value. That is, until our cost function converges. And this is how it will work. This is what will happen if we take one step at a time downwards. We will keep on moving one step at a time closer to our green mark. And why is this happening? Why are we going down correctly? Because this term here, which is our alpha times gradient, is basically helping us go down the mountain one step at a time. Now you might ask me, how does the algorithm know that the minimum has reached? It can keep on updating its position forever, right? No, because when we reach the bottom of a mountain, there is no more room for us to descend any further. The surface is flat, and we know that the gradient for a flat surface is zero. Hence, this gradient term in our equation is zero, and our equation becomes like this. And since the updating term in itself becomes zero, the position won't change after this. And this is when gradient descent will know that there is no need for further update, and it will stop the minimum and has converged. Now let's connect all of this together and see how gradient descent helps us bring our model error, that is a cost function, down to zero, and how this in turn helps us achieve our goal to turn our initial model, that is our red line, to our best fit blue line. So let's see this in action. Amazing, right? Now, with every step we are taking towards reducing our cost function, our model parameters A and B are updating, and slowly our model starts representing more and more like a best fit blue line. So, this is the magic of machine learning that we keep hearing about. And right now, I feel like a magician who has just revealed their trick. Now, before we go any further, let's take an aside on the learning rate. Now, as I mentioned previously, learning rate is basically the size of the steps that we take when we climb down the mountain. So, how do we decide what the size of our steps should be? Now, obviously, we want to take larger steps so that we reach the minimum as soon as possible. But if our steps are too large, then that might lead to divergent behaviors like this. So, if I'm here and I take a very large step, then I might end up here. And instead of going down, I am going up. And we don't want that. Hence, we don't want our learning rate to be high. Then instead, let us choose a very small value of alpha and take really small steps. However, if we do that, then it would take us forever to reach the bottom of the mountain. That is, our model will train so slow. And we don't want that either. So that's why choosing an optimum learning rate is extremely important so that we neither go too slow nor in the wrong direction. Now, the choice of this learning rate alpha actually depends on our cost function, of course. And this comes under the preview of hyperparameter tuning. And we will take a look at how we chose this rate in the final session of our series when we work on improving our model. Wow, we are done. We have learned how our machine learning model trains under the hood. To summarize, we first decide on what our model is and what we are learning. In our case, our model is the straight line y is equal to a plus bx, and it wants to learn the values of a and b to get our best fit blue line. Then we define our cost function, which helps us keep track of how bad our model is doing. In our case, it was simply the mean error, and we wanted to minimize this error so that our model performs its best. We use our labeled training data here to tell us whether we are going in the right direction or not. And finally, we looked into one of the optimization algorithms, that is gradient descent, which helps us minimize the error on our cost function. That's the process of almost all machine learning algorithms. Obviously, the nuances will change. That is, we will have a different way of representing our model instead of this line. And depending on our problem statement, we might choose a different cost function also. Then we might use some other machine learning optimization algorithm to minimize the error. But the process in itself stays the same for any model. That's it for today's session. I hope this has helped you understand how a machine trains under the hood. what we learned today will form the basis of your understanding to further deep dive into other machine learning algorithms. And most of them follow the same chain of thoughts with a difference in implementation, of course. If you're further interested, I highly recommend taking the machine learning specialization on Coursera by Andrew Ng, as it will help you understand most of the supervised and unsupervised algorithms and the basics of reinforcement algorithms as well. As promised, for our next session, we will conclude our series by looking into how we can improve our model's performance now that we have trained it. And this will cover the basics of hyperparameter tuning. We will also be looking at what our machines are learning from the data that we are providing them, intentionally as well as unintentionally, and talk about how that is exposing a lot of our biases. Now, to pique your interest, take a look at this Google translation model. First, I translated "she is a doctor" from English to Hindi, and it gave me an output, "वह एक doctor है." Then I copied the same sentence verbatim and reversed the translation. Look at the output. It says "he is a doctor." It's the same sentence, but it still says "he is a doctor." And it will say that every time. That's something that the model has learned from our data unintentionally, which has a hidden connotation of a gender bias that only men can be doctors. In fact, you can go ahead and see for yourself and also try translating "he is a nurse." And you guessed it right, the model has formed a gender bias there as well, that only women can be nurses, and it will give you a similar output. So we'll conclude our series by taking a look at why managing these biases is necessary while training our model, and how they need to be handled to avoid unintentional outcomes. So don't miss it, because I have saved the best for the last. That's it. Thank you so much again. And over to you, Swati, if you have any questions.
Sure. Thanks, Priyanka. Thanks so much for such an interesting session. And of course, can't wait for the final session in the 3-part series. I mean, machines and biases, that is something that is truly to look forward to. But before we end the session, we do have a couple of questions that have come in. So the first question is that, since data is essential for training machine learning models, how do we even begin gathering our data?
Okay. I think the first step, even before we begin training our model, is to actually define what our problem statement is. Like for the example that I used in the session, the problem statement was to train a model that will predict sales given my marketing budget. Now, what you're trying to solve defines what data you will gather and how you will use it. So if you work at an organization, then you have your in-org systems already that has been gathering a lot of data, like maybe the employee data or any sort of operational data, maybe like customer orders and stuff like that. Now, depending on what you want to train your model for, you can gather the data from these systems. Now, if your org is relatively new, like maybe you are in a startup or something, then obviously you don't have this data beforehand. So that's when you can look for data sets that are readily available on the internet. Now, there are a lot of good sources out there which can help you get a head start on gathering data, like particularly government websites or any public data that is available within your industry and stuff like that. However, like as a startup, I think it is more important for you to set up these systems that help you record the data. So, it's okay if you don't have data on day one, but you should build your in-org structure and systems in such a way, start gathering data, and you do have it ready for use on day two. So that would be my suggestions. Yes.
Right. That's great. Now, the second question is that, given if I have ample data and also a well-defined problem statement, right? So how do I choose which machine learning algorithm to use for training the model?
That also depends on what you're trying to solve. Like, it actually falls down to the problem statement itself. So, machine learning algorithms mainly fall under two categories. So there are regression models and classification models. So classification algorithms are the ones which have a yes no type answer, more like a categorical output. So like, is this a cat or a dog, or do I have cancer or not? So these are classification problems. Now, regression problems, on the other hand, they help you tackle more quantitative issues, like, given the marketing budget, what would my sales be? Or what is the price of this house given I have this information? So the output is a continuous quantity in regression. Now, depending on your problem statement, you will either choose a classification or a regression algorithm. So that would be your first check. Then within the specific type, like maybe regression, there are many algorithms. And how you choose regression algorithm A versus regression algorithm B, then comes down to what kind of data you have. Like, if I have only single input and output, then I might go with linear regression. If I have multiple input variables, then maybe I do PCA and reduce the complexity of my data and then do multiple linear regression. So obviously, like, there's an element of judgment here involved. And that's why most of the times, like, uh, people usually try training their data using multiple models, not just one. And then they choose among like the best one. And of course, like, the amount of experimentation that you will be able to do with your training data, it depends on how much resources you are able to spend on, right? Because machine learning is resource heavy at the end of the day. But yeah, like, that's the gist.
Great. Thanks, Priyanka. I think, these are the questions that we had for now. But in case any of you have any other questions, please feel free to add them in the comments and we'll be happy to address them later. But before we conclude the session, I would really like to thank Priyanka for such an insightful session. And also a big thank you to all our viewers who tuned in for this session. And we really look forward to having you all with us in the next session of Accolite Digital Connect. Thank you so much.
Thank you.